Hey, this is Akash Joshi. I'm the Operations Research Guru, and today we're going to be taking a look at part two of our optimization with calculus um, video. So remember that this video is going to cover all the optimization all the optimization experience or all the optimization problems that you'll need to know for the AP Calculus BC, AP Calculus AB exams, or Calc 1 and Calc 2. So, yeah, let's get into it. In part one, we explored problem A, problem B, and now we're going to look at problem C. We're going to take a look at problem C. So, let's look at the problem here first. So, a rectangle is drawn with sides parallel to the x and y axes as shown below. What is the maximum possible area of the rectangle? So, we can see that this rectangle here is enclosed by these two parabola-like shapes, and the functions for the parabolas are given. So this rectangle, they're just giving a demo rectangle. It doesn't have to be that rectangle. Like, the rectangle can also be like this. Basically, we're just trying to find the correct rectangle that maximizes the area. So first, let's look at our solution, and then let me walk you through it. Okay, so let's set up a area formula first things first. So we'll call this x, and the height will be this right here. We can't really call it y because y would be like the specific point, but we can call it h, and then we can derive an expression for h later on. So the area is going to be 2x, so the entire width of the rectangle times its length, which is its height. Okay, so how do we know what this height is? Let's derive an equation for it. We're going to take the top function and we're going to subtract it from the bottom function. And basically, for any value of x, this will give our height for yeah, so this will give us our value. This will give us our height value, this expression over here. We just do top minus bottom, and we get the height for any specific x value. And yeah, okay, so then what we can do is we can plug that back into our area formula. We do some expanding out, we get this expression right here. We take its derivative, set it equal to 0, as I explained why we do that in the last video. We find the x value, x equals 2 over root 3. And the second derivative test shows us that x equals 2 root 3 is the location of a relative maximum, since once you plug in x equals 2 root 3 into the second derivative, which is negative 18x, you get a negative value, which negative values are less than 0, so then you know it's a relative maximum. And you can go watch a different video for the second derivative test, which basically explains that explains how you know if it's a relative maximum or relative minimum, or it offers a proof for why negative values in the second derivative test correspond to relative maximums. Okay, so yeah, so now we get x equals 2 root 3, and we set it equal, we say it's in relative, we say it's a relative maximum. And once you do that, you just plug it back in here to get the area. So a equals 2 times 2 root 3, because that's our x value. And then we multiply by the height, and the height is given by this equation right here. So we plug in everything over here. X squared, x is 2 root 3, so 2 root 3 squared is just 4 over 3, which is how I got that 4 over 3 over there. And you get this equation, you evaluate, and you obtain 16 root 3, and that is the maximum possible area of the rectangle. Okay, on to the next problem. Okay, this one is going to be a distance problem. Okay, so here's the problem. Find the point on the graph of y equals root x closest to the point 3 halves comma 0, and find the minimum distance. Okay, so this, you might think that's the minimum distance, because if it was a triangle, then that would be a right angle, and by Pythagorean theorem, we know that this is a straight line is the shortest distance. But the thing is, this is kind of curved, so this line over here can also be shorter than this line, so we don't really know. We can't really look at the graph and determine which point yields the minimum distance. So let's look at our solution and I'll walk you through it as per usual. Okay, so we start off with the Euclidean distance formula. D equals the root of x1 minus x2 squared plus y1 minus y2 squared. We plug in everything that we know. We are given this point over here, 3/2 0, so we can set that as our second coordinate, x minus 3/2 squared plus y minus 0 squared. And maybe what we can try to do is we can try to solve for x and y because that's our other point that yields the minimum distance. Once we expand this out further, we really get y squared over here. And if you notice, y squared is just x. So that's how I got this final thing over here. And for optimization problems, if you don't want to take the derivative of this entire square root thing, because that'll probably be kind of complex, you can just take the square root, or you can just take the derivative of this function over here without the square root, because really if you're trying to minimize the distance, the square root really won't do anything since it'll still be the same value. You'll just need to square it back. So yeah, so minimizing the distance is the same thing as minimizing the thing in the square root. Okay, so let's set f equal to that thing in the square root. F equals this. We expand it out, we get this quadratic over here. We take the derivative, f prime equals 2x minus 2, set it equal to 0, get x equals 1, y equals 1. And that is our point. We can plug it back into the distance formula over here to obtain the true minimum distance. And yes, this is our true minimum distance. And always be careful. Make sure that this point, x equals 1, y equals 1, make sure that the second derivative test confirms that it is the relative extrema that you're looking for, as I explained in the last part or in the last video. Okay, that is it for today. Oh wait, no, we have another problem. Okay, let's go over volumes. All right, so we're gonna find the maximum volume of an open box made from cutting off squares of equal size from a square piece of cardboard that measures 48 centimeters on a side. Let's draw our diagram right here. Let's look at it. So we have a square, 48 by 48. We're gonna cut off squares from this square of equal dimensions. They all have dimension x, or length and width x, and then that'll yield a cardboard structure, a cardboard shape that we can fold up into a neat box. So what are we trying to find? We're trying to find the maximum volume of the box that we can make after cutting off a specific length of a square from this 48 by 48 square. So let's create the function, the objective function, volume. So volume is equal to length times width times height for this rectangular prism technically. And so the length and the width are going to be 48 minus 2x, because that'll yield this little part right here. That'll be the length, and it'll be the width on the other side. And then our height is just going to be x, because if you imagine with your using your brain, you can kind of picture it in your brain and see that once we fold this upwards, the height will just be this x. So yeah, that's how we get this expression right here. We can expand it out for ease, and we get that over there. Take the derivative of v, and we get 12x squared minus 384x plus 48 squared. We can simplify, we can factor out 12 to make it a bit simpler, and then we can factor it into this right here. And then finally we set it equal to 0. We get x equals 8 and x equals 24. X equals 24 doesn't really mean anything, so it doesn't matter if we get two solutions, because x equals 24 is irrelevant, since if x equals 24, that means this is 24 and this is 24, so we're just cutting out the entire box, and that doesn't really make sense. So that's why x has to be 8. Okay, so v double prime, using the second derivative test, when x equals 8, v double prime is going to be less than 0. So x equals 8 is the location of a relative maximum. We confirmed that, so now we can go ahead and plug it back in. V equals 48 minus 28 squared, or minus 2 times 8, and that quantity squared times 8. And we're just plugging in 8 into this equation over here once we found our x value. And that yields 8,192 centimeters cubed. And yes, that is our maximum volume, maximum possible volume that we can make from an open box where we're cutting off 4 sides of 4 squares from the box out of the corners. Okay, that's it for this video. Thank you for listening. See you next time.